Hello, everybody. Welcome to Lesson 2 of the atom and the chemistry unit in the Science 20F curriculum. So for this second lesson, we're going to start by breaking down the atom. So this is a part that we might have learned at a previous time, but if it's been a while, that's okay too. So there are three parts to the atom that we discuss in this unit. There is the electron, also noted with like an e to the negative, like with a little negative exponent on it. This electron is one of the smallest particles that we have that has mass. So it's very small. It has a little bit of mass, almost zero, extremely small mass, essentially about zero mass. And it has a charge of -1. This is a fundamental charge. All charge that we know of in the universe, we kind of reference to this charge value. So a single electron has a charge of -1. Electrons in our model of the atom, the electrons are found outside. They're found in sort of a cloud. I like to go with a cloud sort of idea in a space around the nucleus. In the middle of the nucleus is another unit. Let's go with blue maybe for this one. And this is another part of the atom, and it is known as a proton, or P+, and it is found in the center. So it is found directly in the middle. Let's just turn our nucleus blue so we can make that. So it is only found in the nucleus. It is not found around the atom, and it has a mass of 1 atomic mass unit, so 1 AMU or 1 U, which means it has mass. It's a lot more massive. It's a lot. I think it's like 10 to the 17 times more massive than the electron. So lots and lots of zeros there. And then a proton has a charge of +1. Okay. So now protons are still very light. There are 6.6 times 10 to the whatever, 34 or something, time of them. You need that many of them to make 1 gram, but they are still a lot more massive than the electrons, which are thousands and thousands and thousands of times smaller. Now, this is really important, is notice that for electrons are negative and protons are positive, and they're exactly equal but opposite. Equal but opposite charge. So the equal magnitude but opposite in nature. Neutrons, on the other hand, are sort of the last element, the last part of the atom that was ever found, and it is a neutral species. It is essentially a proton that lost its charge. So it has the same mass, 1 atomic mass unit, but it has no charge. So it is sort of a balancing act. And they are also found in the nucleus. So if we want, we could put sort of a little gray dot, and we could say that this is also in the nucleus. So this is the model, this is the perspective we take on the atom, and one that will hold all the way through university chemistry, is essentially based on this Bohr-Rutherford model of the atom. And so in the Bohr-Rutherford model of the atom is mostly empty space. A positive nucleus contains 99.9% of the mass, but less than 1% of the space. So let's look again at our diagram. Remember that the electron has a very small mass, essentially 0, and the electron occupies this whole big red circle I drew. But the proton and the neutron are simply occupying those little dots that I made, and those have thousands and thousands and thousands of times the mass of that electron. I'm going to double check my mass of electron proton just to... Oh, it's 1,836 times the mass of an electron. So let's just put that up here. That's a nice little fact. So mass of an electron is you would have 1,836 times the mass of electron equals the mass of a proton. So that's kind of gives you an idea of how much smaller, like close to 2,000 times smaller. So think about trying to pick up 2,000 pounds versus picking up 1 pound. Pretty big difference. Certainly, I'm okay with picking up a pound. I am never going to be able to pick up 2,000 pounds. So picking up a car versus picking up a can of soup, that's the difference in the mass of a proton versus the mass of an electron. So that means that this outside shape, this giant shape really, this big space, that's 99% of the space, but only one electron is there. So, and versus the inside of the atom, which is where all the protons and neutrons are, but that is a really, really tiny spot, a little tiny space. So in this model of the atom, we have to imagine that we have these really tiny space in the middle that has all of the mass, and then we have a larger space around that has all of the electrons, and it's all the volume. Now electrons are negative and protons are positive. So because like charges attract, or like charges repel, and unlike charges attract, we can kind of make this idea that this positive center of the atom is actually attracting these negative electrons inwards. But because those electrons are so tiny, they can't stop moving. They essentially can't stop moving. So they're so tiny, they have so little mass that they can't stop. We can't stop their flying around, zooming past, or they can't stop. The smallest they can get is actually not as small as the atom's nucleus. So we have a lot of like different ways that the atom has been explained. This is a good example of 1, 2, 3, 4, 5 of 5 different models for the atom. 6, I guess, or 6 different parts of the atom model. And this is to give you an idea that that atoms have evolved, or our understanding of the atom has evolved, our model for it has evolved, and we can see this as how science works. Even in the current pandemic, we've seen the evolution of science before our eyes. The initial models for the virus suggested that masks would not be effective, but now the new evidence shows that those countries that used masks right away had much lower infection rates. So this indicates that this is that whereas the model had originally said, well, viruses are very small, they shouldn't be, masks shouldn't stop them. We didn't realize at the time that this virus was largely being transmitted inside of droplets, and those droplets are not small, so a mask is a very effective way to stop it. So our understanding of science evolves all the time, and that's kind of a key concept of understanding science, is that science is about revising our ideas. So Dalton, for example, suggested the atom could not be divided, but he did make the correct assumption that that matter was made of atoms, but assumed that those atoms would be indivisible, not able to be divided further. Thomson then went on to say, well, I've got some experiments that show that there might be positive and negative parts. So now the atom was proposed to be made of a positive sort of slime that kind of held together these negative charges. Then Rutherford said, well, wait a second, why don't, what if all the mass is in the middle? And so he developed the idea of the nucleus. And then Bohr said, well, if the atoms are in the center and the electrons have sort of light-like characteristics, maybe the electrons should be organized in sort of shells. And then Schrödinger came in and said, well, shells are good and all, but they don't explain everything. Why are some atoms of the same element heavier? Why are there differences in other ideas? And so he brought in this new idea of subshells that we won't cover till grade 12, really. And then Chadwick was said, hey, these are neutrons. And actually, you know what? There's a little mistake here. This should be down here, because that's that's what's being answered by Chadwick's model, is that why are some atoms of the same element heavier? Interesting. Okay, so atomic theory, this is the historical development of the model of the atomic theory from Dalton to Chadwick. So when we talk about an atom, there are a couple of values we should consider. One is the atomic number of that atom. The atomic number is determined by the number of protons in the nucleus. The atomic number is special because not only is it the number of protons in that atom, it also identifies that atom as a particular element. Every single one of the element names you know is a name that corresponds to a specific number of protons. The number of protons determines the element. Number of protons determines the element. So all we need to know is the number of protons, and that number of protons is the atomic number. So this is also the number of protons. The mass number, this is the number of components that have mass. And by that I mean the protons and the neutrons. Remember that those are the only two that actually have atomic masses that we can detect, one atomic mass unit each. So all atoms have a mass number. The mass number is equal to the number of protons plus the number of neutrons. So the total, so mass is equal to P plus N. Notice I do like these symbols. I like the P plus to remind me that it's got a positive charge, and 0 to remind me it has no charge for neutrons. Since a proton and neutron each have a mass of 1, the atomic mass of one atom of carbon-12 would be 12 atomic mass units. The atomic mass of an atom is expressed in atomic mass units, and so for carbon-12, it will be 12 atomic mass units. Mass number can be expressed as a number with no unit, and the atomic mass is expressed using the same number with a unit. So mass number can be expressed as a number with no unit, 12 for carbon. The atomic mass is expressed as the same number with a unit. So atomic mass is referencing the actual weighing of the object. The mass number is to suggest how many nuclear particles are there, how many subatomic particles. So solving for atomic number and number of neutrons can be found by modifying this equation. So for example, the number of protons could be the mass minus the number of neutrons. That would also work. And you could find the number of neutrons if you wanted to from the mass subtracting the number of protons. Okay. So in the next section, we'll go through some of the ways that we're going to calculate these different parts. So the first thing we have is the number of protons. This number of protons is equivalent to the atomic number. And we can find that atomic number. Usually it's given from the periodic table. Sometimes it's represented with this sort of Z. It's sometimes drawn like a sort of a fancy Z. It's very similar to the integer symbol that we use in mathematics, but overall we're probably not going to be working with that in this class. The next is the number of electrons. So because the protons are positively charged, the number of electrons for a electrically neutral atom has to be equal to that number of protons. So once you've figured out the number of protons, which you can get from the atomic number, then we know that the number of electrons has to be the same. And that's simply the fact that we are talking about electrically neutral, reminding ourselves that protons are positively charged, electrons are negatively charged. So if we have some protons and we want it to be neutral, we need to have an equal number of positive and negative charges. to determine the number of neutrons, we need to think about how the total mass of the atom is equivalent to the number of protons and the number of neutrons together. So the mass will be mass subtracted the atomic number will give us the number of neutrons, and that's because the atomic number is equivalent to the number of protons. So we're really saying that the mass minus the atomic number, or minus the number of protons, is equal to the number of neutrons. So now we've got all three atoms. The atoms are fully described in this way. We can say that the number of neutrons is calculated from the mass minus the atomic number. Number of protons is directly equal to the atomic number. Number of electrons is equal to the number of protons, or equal to the atomic number in a neutral species. So 3 rules. P, protons equals electrons equals atomic number. We can get the mass number by rounding off the atomic mass so that it's an integer, no decimal places. We don't need those in this class. We can use the mass number minus the atomic number to find the number of neutrons. And if you know the mass number and the atomic number, you can find the number of all 3 subatomic particles. Okay, we will continue this in our next video.